So in this week's presentation, we're going to be looking at lactate and ventilatory thresholds. So we have been looking at, over the last couple of weeks, our oxygen consumption and uptake. So now we're going to switch over to some other variables which can be useful in assessing endurance performance. For this presentation, there are a couple of key takeaways that I want you guys to be trying to follow along and pick out as we move through. The first one is be able to define the lactate threshold, obla, and the ventilatory threshold. Second, we want to be able to outline the methods to measure these three things. Thirdly, you need to be able to interpret test results and identify the thresholds on a graph or a set of data, basically, and understand how these thresholds can change with training, so how they adapt to chronic stimulus. So remember the difference between chronic and acute adaptations, and then understand how we can apply threshold data to prescribing training intensities. A lot of different terms that you see floating around in relation to lactate thresholds and lactate training, such as the lactate turning point, the lactate break point, the aerobic threshold, maximal lactate steady state, obla, individual anaerobic threshold, and the lactate threshold. The two that we'll be using is obla, the onset of blood lactate accumulation, and lactate threshold. But just be aware that if you see any of these other terms in research or in textbooks, for the most part, they are referring to one of these two terms as well. The different things we do to measure our blood lactate levels. The first one is, you can see pictured in the bottom picture there's a little blood sampler which you guys would have seen used for doing your blood glucose and possibly your blood cholesterol. I'm not sure if you guys do that in first year anymore. But yes, so we measure our blood lactate levels, and then we take that over a series of increments as exercise intensity increases, and then we plot that data onto the graph so we can look at it visually, so we can then start to identify these turning points. But usually the lactate turning point is the point where the blood lactate increases of around 1 millimole above the baseline level. So that's about seeing where it's kind of flat at towards the start of that graph, and then where it goes up above 1 millimole above normal, and then obla is usually considered to be 4 millimoles per litre of blood. With lactate threshold, it normally means that we've started to accumulate some lactate in the blood, but we're in a range where we can continue and maintain the exercise intensity as long as we don't increase it drastically. When we're working in obla, we're usually expecting that we're getting to a level where we can only maintain that exercise intensity for less than an hour if we were staying at or just under that obla. So we're accumulating blood lactate, but it's at a level that can be maintained. As soon as we go over obla, that becomes rapid onset of blood lactate accumulation, and that exercise intensity becomes exercise duration at that nil intensity becomes rapidly decreased, and because we see that lactate accumulating so quickly that it impairs our ability to continue exercising. Briefly discuss the application of lactate threshold and obla. So Powers et al. In 1983, this was a pretty old study now, but it kind of set the baseline for why we apply this, found that the R number, so in statistics we will have talked about this, or maybe we haven't. If not, we'll be talking about it soon, is essentially the level of correlation between two variables. So the closer it is to one would be an exact correlation. So this thing in 100% of cases predicts this other thing happening, so an independent variable, found that when we look at the lactate levels, that it's about 0.94 in terms of predicting someone's performance in a 10-kilometer race, which is a pretty high level to find. Whereas when you look at someone's running economy and their VO2 max, you can see that those numbers are much lower, which means they're not as effective at predicting someone's 10-kilometer race times as their lactate levels. The following study found something very similar, found that the lactate levels were not quite as correlated when it turned to a 5 kilometre range, but still much higher than the other two. So something to be aware of as to why you'll see lactate training be used as a measure of how to improve someone's performance, and as a regular testing method alongside your classic things like VO2 max, is because it seems to have a higher correlation to someone's actual race day performance. Changes in the lactate threshold in response to training. So this, for a sedentary individual, we see that their lactate threshold is usually reached between 50 and 60% of their VO2 max. Whereas when we look at an endurance trained interval, that gets pushed all the way up into the 70 to 80% range, which means that someone can work at a much higher VO2 max consistently without accumulating lactic acid with training, which can massively improve their endurance performance. Building on the last slide, you can see that there are two different graphs here. On the left we have blood lactate versus VO2 max, on the right we have blood lactate versus treadmill speed. The untrained is represented in red and the trained is represented in blue. So in both cases, training pushes that graph more towards the right side. So we don't start to accumulate blood lactate levels until a higher VO2 max after training, which we just talked about, which can be represented as treadmill speed or exercise intensity. So the higher we can get that exercise intensity without starting to accumulate lactic levels, the more easily we can continue to perform at a high endurance level. Because remember, once we start to go past that optimal level, we see that rapid accumulation of lactic acid, giving us an imminent time before we cannot maintain that intensity. So we want to be able to work at the highest percentage of our VO2 max or highest exercise intensity as we can without accumulating that blood lactate levels, which means if we're measuring it, we can see where those turning points are and use either the exercise intensity that they occurred at, the heart rate that they occurred at, or the VO2 max that they occurred at as training variables to try and train in that range without having to constantly stab ourselves and check our blood lactate levels. Thing that we do see is that as that blood lactate level is pushed to the right side as we are training, so you can see that on the bottom two lines there, the white circles representing pre-training, the black circles representing post-training. So as our blood lactate levels get pushed to the right post-training, so that blood lactate levels aren't accumulating at a lower intensity, we can also see that that means in those top two lines that our heart rate, sub-maximal heart rate at a given intensity also decreases. So the question is why? And the most probable answer for that is because, remember, our circulatory system is not only just used to circulate oxygen to the tissues, but also circulate CO2 out, and that increase in ventilation is usually due to acidosis of the blood. So if we're not accumulating as much acid in the blood, the heart isn't having to work as hard to circulate that acidity to the lungs and then buffer it with bicarbonate to turn it into CO2 and water to excrete that CO2. Ventilatory threshold is another important factor to consider, which is also primarily driven by the accumulation of lactic acid. So as we know from last week, our oxygen consumption and exercise intensity share a linear relationship, which means as our exercise intensity goes up, our oxygen intensity will go up at this in line with it until we hit our VO2 max, obviously, where it plateaus off. Our ventilation, however, does not go up linearly like you would expect it to, because we think of our ventilation, breathing in and out, as our primary way of getting oxygen in and out, but it's also our primary way of excreting CO2. So once we start to hit that onset of blood lactate accumulation, we also see a rapid increase in the ventilation threshold of ventilation, which is represented on that graph there. So it's still a linear relationship, but it has a turning point, usually in line with the obla, and then that starts going up. And that's because as our CO2 levels start to massively accumulate in the blood, because remember that lactic acid or acidosis of the blood gets converted into CO2, it stimulates the brain to start breathing more rapidly. So we start to breathe out much more quickly to try and accumulate for that CO2 rather than accommodate for the oxygen consumption coming in. So that what we see is that change from primarily trying to get oxygen in to primarily trying to get CO2 out of the body in line with that lactate levels. So, what question for you? Why would taking baking soda help to improve exercise and performance? If you want to have a guess, pause the video now. Otherwise, I'm going to go into it. So, baking soda is bicarbonate. We know that bicarbonate buffers lactic acid and turns it into CO2, which we can easily excrete through breathing. So if you are able to stomach taking pure baking soda, or bicarbonate, NaCO3, you can take it, and then if it is into the bloodstream, it can buffer higher levels of lactic acid, which means we can start to accumulate, or not start to, we will be able to clear more lactic acid more quickly for a certain amount of time, which will push that lactate threshold and that onset of blood lactate accumulation, OBLA, even further to the right, so we can work at a higher intensity again before we start to accumulate that lactic acid, which is highly correlated with our failure to be able to continue in exercise intensity. We can see oxygen uptake, and we can also see our ventilation. So you can see oxygen goes up relatively linearly until it starts to plateau off as we're reaching our VO2 max, whereas ventilation goes up linearly, hits that turning point, which is represented as the ventilation breakpoint. So ventilation breakpoint and ventilatory threshold are the same words. So remember what we talked about earlier with there being different words for lactate threshold. Same thing here. So the lactate breakpoint is the lactate threshold, the ventilatory breakpoint is the ventilatory threshold. So that once we hit that breakpoint, it again turns, goes up relatively linearly again, but just not on the same line as it was going before. And that's also good to remember as to what you're looking for when you're looking for that graph for lactate threshold and OBLA. So we talked about the actual millimoles per litre that you needed to look for with lactate threshold and OBLA, but remember, lactate should be a flat line, goes up a little bit on more of a slope. Lactate threshold, when it starts to go up in a different direction again, that turning point will be OBLA. Summary, guys. So a lactate threshold is the critical intensity where lactate starts to accumulate above resting levels. So up until that exercise intensity, it stays basically in a flat line. Once we hit that lactate threshold, or lactate turning point, or lactate break point, whatever you want to call it, our rate of production is now exceeding the rate of removal from the body. So we start to go up again, still on a linear line, but just not a flat line anymore. We're now going up on a little bit of a slope. It is usually measured by determining our blood lactate response to exercise. So similar to a VO2 max test, we'd put you on a treadmill every couple of minutes. We'd take your blood lactate and push the exercise intensity up a little bit, and we'd just keep doing that. If we get to go back into the lab at some point in the future, hopefully I'll be able to get you guys to actually do that and your VO2 max. And then OBLA is identified as the intensity where lactate reaches 4 millimoles per litre, which is our second turning point. So it's still a linear relationship, but this time it's turned onto a new slope. So that's what makes it look like a curve. So we have 3 straight lines where it turns to that third straight line upwards is our OBLA, our onset of blood lactate acid accumulation. As soon as we go above that OBLA intensity, it starts to accumulate rapidly and limits our ability to continue performing endurance activities. Our ventilatory threshold is closely linked with our lactate threshold. So remember, once we start producing more lactic acid than we're able to remove, our breathing rate starts to rapidly increase, or our ventilation. So we can start to clear that CO2 rather than following our oxygen consumption as you'd initially think. So once we start to have above baseline lactate levels, our ventilation will start to go up. So it goes in line with our lactate threshold. As we train for endurance performance, threshold relative to VO2 max and exercise intensity, and heart rate all change. So it gets pushes to the right, so we are able to work at a higher submaximal VO2 max without the accumulation of blood lactate levels, improving our endurance and our high intensity work as well.